Welcome back to Ox Tools. I'm Tom. So what we got today here, this is kind of interesting. This is a Johansson comparator stand, and this was sent to me by a viewer who wishes to remain anonymous. But anyway, this came all the way from Sweden, believe it or not, and it's an original CEJ Johansson comparator stand. So this thing's built like a tank, let me tell you. It was missing a piece, which is what this video is about. We're recreating the anvil that was missing. And we have some machining in this video, and you guys will get to see machining this thing. But we should look at some of the design features of this, which are kind of interesting and notable. And then we have the proper indicator that goes in here as well. So it's got this large 30mm shank. Let's just do the whole thing here while we're at it. Okay, so that's kind of the general layout. But let's take a look at some of the design details. All right, the first thing I want to point out, let's take this out of here. Set that aside. Hopefully you can see in there. Let's see, maybe I can just pop that off and you can see, okay, there you can see it a little bit better. So what they've done, and this is actually a really nice trick here. So you saw that slides on this shaft here, but what they've done is they've relieved the center section here. And the reason for that is that's where the clamp screw is actuating on. And what they want, and this is correct, is they want it to clamp on these outer edges first before the center section, and that gives you the most rigidity when you use one locking screw like that. So it's actually just a subtlety of designing a clamping mechanism like that, and there you can see they've done it in there as well. And it's just a nice touch. I noticed it and I went, oh wow, okay, that's great. So what that means is there's kind of a minimal sliding area, right? But when you lock this down, it locks, and there's no wiggle in that direction. Okay, kind of neat. Then, well, let's we'll go down and we'll take a look at this anvil too. All right, so here's the anvil. Now this is the new one that I made, and like I said, you guys will get to see the machining work on that, in a few minutes here. So what we have here is we have a Platen, and then it has some locking screws here, and you can see that they're cone point, and then those reference with those little notches there. And in the video we show how to accurately position a V or a notch like that in relation to a corner, and that's one of the machining content of this video will show that. So that's kind of neat. And then it has a fine adjust mechanism down here, and let's pop that out of there. So, and there's the relief thing again there. Let's slide this aside. So it's got this is like a micrometer screw here, and it acts on the bottom of this, and that's how you make your fine adjustment there. So instead of a rack and pinion or some, I don't know, kind of awkward setup there, what's nice about this is it's all acting right on the center line. So we lock that down, we leave that loose, and then we make micrometer adjustments here to null the indicator out. So pretty cool. So what do you say we look at some machining content on how to position grooves, and then we got some surface grinder action here doing these long skinny little slots, so don't get to see that very often. All right, so what we're doing now is we're cutting these V-grooves here, and these retain the Platen in the instrument and also allow you to put some accessory pieces on the working side. So what we want to do is we want to actually position these accurately in relation to the edge, and also we want the depth to be correct too. So instead of tipping the head, I despise tipping the head, we're just going to do it in a V-block like this. and that's how I did these two here. Okay, and then we just come in, oops, sorry about that. We just come in from the side, and that's actually a 90-degree angle in this attitude here. So the trick is, since we're moving in X and Z, is to get the theoretical intersection of that cut in the right spot. So that's what we're going to show you, or that's what I'm going to show you how to do. So first off, I want to lock this down in the vise, just so it doesn't move around on me. And I like using these old school parallel clamps for that. So for those of you that haven't used these before, they're actually pretty nice. And oops. So when you're opening and closing them, you hold on to both levers or both knobs at the same time. Then you get it so it just fits. And then to do the tightening, you just use the rear one here, or the one farthest from the jaw, and that does the business there. And you got good leverage against that. Let's do this side here. So you just get it to just slip on, and then snug that rear one, and that tips it just a little bit, and then that sucker's in there good. So okay, all right. We've got a carbide end mill here, and it has a corner radius on it, which further complicates what we have to do, but it's not that big of a deal. And I've got some layout lines on here, and these kind of guide us in the roughing stage. And when we get a little bit closer, we'll start taking measurements, and then we'll make adjustments with the Z and with the X to get the groove in the right place. So let's lock that in. All right, and I'm gonna start making some cuts. Like I said, these scribe lines guide our initial cutting, so that we're in the kind of the right spot. So you can see that cut there is fairly high, so we're gonna just nick in a little bit. So and that's probably good. That'll probably work. A little liquid love on there. Okay, so you can see our scribe line, our upper scribe line and our lower scribe line. Now, these are put in with a height gauge. And so they're reasonably accurate. So we got a little bit left on the bottom one, and we got a little bit left on the top one. So we're going to sneak in a little bit more. I'm going to move in on X, since it appears that the gap between the cut and the line is smaller on this side than it is on this side. So I'm going to move in this direction, okay, a little bit, and get that centered up. And then we'll take a proper measurement with a pin and some micrometers. So, without further ado, creep in a little bit. And it looks pretty good. All right, we're going to measure the position of our groove, and we're going to use a gauge pin of a known diameter, okay, and we're just going to sit that in there, and we're lucky it kind of stays. So I'm going to take a dimension over the pin and over the block. Oops. Over the rainbow. Let's get that in there. I got a groove on the other side, so I got to be a little bit careful here that I get a good, it doesn't feel good. There we go. That's better. I got to catch the pin and not fall into the groove on the other side. What do we got there? Pin does not want to stay. All right, so I got 1 inch 605, and in that direction, so let's write that down, 1.605. And then what I want to do is I want to measure from this surface down to the pin, and I want to clamp it in this case because I'm a klutz and I don't want to drop the pin anymore. And what I'm going to use for that is I have it's a depth mic, okay, but this is a blade depth mic. And so if you're going to buy a depth mic and you haven't bought one yet, get a blade depth mic. And there's a couple of reasons. One is you can measure the same stuff that you can with a regular round Anvil depth mic. But with a blade, you can get down into a slot or a groove. And then here's the most important part is when I rotate the thimble here, you see it's extending, okay, but it's not rotating, okay? Now this is a big deal. Depth mics are actually kind of hard to read accurately and consistently. And what helps is if you don't have a rotating spindle. The rotating spindle tends to wiggle the base around, and so if you have a non-rotating spindle, it helps a lot. So I got to do this left-handed here. So I'll hold it with that hand, and I'm going to turn it so that alright, that's pretty good. What do we got there? 25 plus 14. That's 134. 134. Okay, so let me write that number down, 0.134. All right, so now we got a little bit of math to do to figure out where that pin is in relation to where it's supposed to be, and then I can actually drop down and move over the correct amount and get that right where I want it. So I was over there doing the math to figure out the position here, and I kind of discovered something kind of interesting in that for the size of this particular groove, the way it is right now, this pin is actually a little bit too big. It's sitting on the corners. It's sitting on the corners as opposed to the flats. It's not actually engaging the flats right now, which when you take measurements based on that, it gives you kind of erroneous numbers and kind of, well, messes with your game a little bit, okay? You know, and what I was doing is I was just laying this out in a drafting program so that I could just pluck the numbers off of the, the drafting program, which is simple. You know, it's a graphical interface and you can kind of see what's going on really easily, and you can pull dimensions from corners and surfaces that you can access. So after that discovery, what I want to do is I'm going to take some measurements with if I don't drop it, a smaller pin that definitely is engaging the groove in a tangent way, which is what we want. So we're going to take a new set of dimensions. Make sure I got it on there right. 31. Okay. And then we're going to do this. We'll do our depth gauge again. Back that off and do the old left-handed whatchamajigger. All right. So 1685. Okay. So now let's go plug those into our CAD layout and see what was actually happening with this pin, because it's actually kind of interesting, and it gets exposed when you have actually a graphical layout of this thing that you can use. Okay, so here's the layout of this thing, and this is this interesting thing that I mentioned over on the mill. These are the grooves that we're doing, and I'm just going to scoot over and we'll zoom in on that a little bit so you guys can see it. So yeah, that looks pretty good. There's our 1/4 inch pin, and it's tangent to our little groove right there, and that's where I came up with the numbers that I wanted to try to hit based on the size of the block and the diameter of the pin. Okay, now let's zoom in on the pin a little bit here. Okay, and what you see here is that circle of the pin is tangent with that line right there. Okay, and now when that groove's a little shallower though, we run into a little bit of a problem. So let's draw a line from that intersection, and that's the tangent point. It's picking up the tangent point, and then we're just going to draw it to the center of the circle. Okay, so you can see there that there's not a lot of room actually where that thing is sitting properly in tangent. So this pin is a little bit big in diameter, in particular when our little notch is a little bit smaller. Okay, so let's see. So there's me. I've set up another scenario there. So let's do this. Let's copy this whole mess here, and we're going to scoot it over here. All right, now let's blow this away. Let's blow that away, and let's blow this away. Okay, and let's see. What are we going to do? Let's rotate this whole mess, and I'm just going to minus 45. Okay, so now it's kind of oriented the way we're working on it. Okay, so let's zoom in on that little sucker right there now. So we took some measurements to this smaller pin. Okay, so what we're going to do is we're going to actually, you know what? Let's let me back up there. I'm gonna place the 1/4 inch pin. All right, to the dimensions that we measured the 1/4 inch pin to. So what I'm going to do is I'm going to do a little offset, and that number is let's see, 0.134. Enter. So I'm going to offset this. This is the surface we're measuring from. All right, and then I'm going to offset this other surface that we were measuring from. Offset 1.605. All right. So all I'm doing here, guys, is saving myself some math. All right. So there we go. And now what I'm going to do is I'm going to draw an intersection. I'm just going to fillet those with a 0 fillet. All right, like that. And I'm going to draw our pin in position now. All right. Now I want a special kind of a circle called a tangent radius. All right. And I'm going to grab that tangent. I'm going to grab that tangent, and then our radius is 0.125. Bink, circle. Okay. So now this is where we've actually measured the circle. Okay. And now you can see this is looking a little suspicious here, isn't it? All right. So if we draw a line from the center of the circle over, we're not even on the cut yet. All right. So what that means that pin is actually sitting funny, and we're measuring it kind of out of position. So the only way that you would kind of pick this up is by doing this in a drafting program. Okay, yeah, you could do the theoretical math, right? But it wouldn't expose where these tangent points are. Okay, and so you could get tripped up doing this purely mathematically, I think. All right, so if let's just take a measurement from the quadrant of that circle right there to that little line. All right, and it's saying 9 thousandths, and then we're going to take another dimension from the quadrant of that to there, and it says 24 thousandths, okay? So it says 9 and 24. But I don't believe that we have the 1/4 inch pin in the right spot. It's in a funny place, all right? And let's see if we can figure out where that pin is in relation to our groove. All right, so let's take a look at the 187 pin case here, okay? We'll zoom in on that so you guys can see it real well here. So this is with the 187 pin case, and what I've done is I position it to the dimensions that we took with the smaller pin, okay? And now this is, it's an abbreviated thing, so it's the distance from the back that we measured with the micrometer, and it's the distance from this surface to the top of the pin that we measured with the depth micrometer, okay? So mainly, I just kind of have this layout already set up. So if we zoom in a little bit more here, what I did was I went ahead, and this red line right here that I'm highlighting, okay, that's the actual surface, the cut surface that we have over there right now, okay? And so what I'm going to do is I'm going to borrow that surface because it's all in relation to the size of the piece here. Actually, you know what? No, what I need to do is let's set up another instance of this. This is easy here. You can just copy this stuff all day long here. So let's just drop another one down there. And let's see, let's get rid of that. Let's get rid of that. All right, and let's kind of clean it up a little bit. Okay. Now keep in mind that this is our 1/4 inch pin here. All right, that's our 1/4 inch pin. And don't sweat the jaggedy. That's just a figment of the video card. I'm just going to hit regenerate here, and then it sharpens it up. Okay. So let's go back over to this guy. And what I'm going to do is I'm going to make a copy of this, the real surface, or the surface that we have right now. I'm going to copy that, and then I'm going to grab that corner as my to relate that to the other piece. So see, I got a piece now that I can whip around. So let's scrunch our way over here. Okay, and then I'm going to use that same corner to reference this new piece here, pink. Okay, and now you can kind of see we got a little problem here, right? So this is that surface that we measured using the 187 pin, but you see here we've got a false measurement where the 1/4 inch pin is, and that's because it's resting on these corners right here. So it's actually pivoting on those corners and not sitting tangent. So this is this is a subtlety, guys. So it's just something that's interesting to me too. And using this tool to analyze the problem, which is really kind of the fun part here. All right. So let's see where that pin really is, okay, in space. All right. So just to get rid of some lines here, let's get rid of that. We don't need the dimension. You guys know what it is, okay? So what we have going on is the red line is our actual surface. So let's just make it our actual surface here, okay? And then so there's where we are, and this is where we want to be, but we're not there yet. So let's just kill that. All right, we're going to get rid of that so it doesn't confuse us here. But you can see as I zoom in on that a little bit, we got a little bit of a problem because we know that pin, which is this circle here, it can't rest inboard of that surface, so it's actually sitting on that corner right there. So let's put it there. All right. So how do we put that there? That's kind of a weird little operation, right? Well, it's actually not too bad because we know that the pin is sitting on this corner as well, right? All right. So let's just do it really simply here. What I'm going to do is I'm going to get in real close so you guys can see it, because this is fun stuff, okay? And this is why it's really nice to learn a CAD program, and just pick one and start learning it, okay? So we're going to draw a line, and I'm going to go straight up, okay? And now what I can do is I'm gonna move our pin from there and have it sit on that corner. Okay, so now that pin is sitting on that little intersection right there of our cut surface and our surface of the block. All right. Okay, now you can still, as we go over here and look, we still got a problem here. So now what we need to do is rotate that pin. We need to rotate that on that corner until it's just touching that corner. So how do we do that? Well, an easy way to do that is I'm going to draw another circle, and from this point right here, all right, and I'm going to draw it to intersect right through there. All right, so now that's the path that this pin is going to move in. All right, so what we want to do is we want to move it from that little spot right there to that little spot right there. So now we just do a little rotation. Okay, let's see if I can get that. All right, so we're going to rotate, and this is the thing we're going to rotate. All right, and the center is going to be the center of that circle. Okay, and it's asking me for a reference, and my reference is the center of this circle to that point, and then my new reference is that point. Okay, now let's get rid of some of this garbage so we can see here. All right, let's get rid of that little piece right there. Okay, so now actually it looks like we're sitting pretty good. So we're sitting on that corner, and I can zoom into the cows come home, and it's still sitting on that corner. Now I come up to this corner here, and it's just touching that corner. Okay, so that's where that pin really is. And you can see here that if we draw a line from the center of this, that's where it would end up being tangent, and we're nowhere near that. All right, so anyways, this is kind of an interesting side excursion there to show some graphical analysis, right? This is totally doable with mathematics, okay, but keeping track of where you are in space by just looking at numbers for us machinist types is sometimes a little bit tricky. It's more helpful to orient the part the way it is in the machine, and then we can pull off references from different areas, and it makes sense to us in context to what we're doing in the machine. Okay, so we're going to switch over to that other pin and continue on here, because now we got some dimensions. We know we need to go X11 and Z22, and that puts our slot pretty much in the right spot. So sorry if this was boring for non-CAD people, but I think it's relevant for people that want to learn and get better at their craft, because this is just a tool like a end mill or a screwdriver. Okay? All right, so we got our new numbers that we extracted via the CAD program based on our smaller diameter pin. So we're gonna move over a good portion of that those numbers, but not all of it. And oops, too much. Let's do 20 on that. Okay. And then we're going to take a final measurement, and then we'll take a look at it. All right, let's get a measurement there. See what we get. We got 184.3. Yeah, something like that. About 2 thousandths off that way. Let's get a measurement this way. Okay, so we're actually 50, yeah, 145, so that's like right on right there, so. Take that one again. This, actually, you know, when it's kind of weird when you have to turn something with the, it's like brushing your teeth with the wrong hand. It feels weird. Okay, so that's pretty much right on. That's on our target number there, which is good. And we're, what did I say? 2 thousandths off of our other one. All right, so let's see, what does that mean? That means if we go, let's just go down 1. Let's see what we get. Let's try that. All right, that's probably it here. $83, that's 1 thou off, so I'm not going to worry about that. You know, the exterior of this block's going to get ground after heat treat anyway, so this is mainly kind of an illustration on how you can position grooves pretty accurately. So, but that's kind of going to be out the window a little bit when we, ouch, when we do some grinding on this. Our other dimensions. So I'm going to try something a little different here. Let's put this over here. Squeeze it. Yeah, I think that's better. See where we are here. Now I can use my proper hand, right? All right, so it's a little bit under. So 145 minus a half or something, or a couple of tenths. I'm not doing any more. That's it. I'm leaving it. And I'm going to zero these 2 axes now, just for fun, because I got one more groove to do. And I'm not going to show that on camera because we got some grooving to do on this, on the surface grinder, which is kind of fun. So we're going to shoot to that next. All right, so we're going to get set up here to cut grooves on this. And for those of you that soldiered through all the all the CAD work, you probably noticed that there's a bunch of grooves from the surface down like that, and that's stock on the CEJ Platen. And the idea is that, you know, when you're sliding a sample around on here, any dust or anything drops into the grooves, and the edges of those channels are very, very kind of crisp and sharp, so they just knock anything off and that's on this, and it drops into the groove. So that's kind of the idea of serrated platens. So what we got here is we have a cutting disc, okay, and this is just aluminum oxide. It's a 60 grit and it's 0.35 wide, so a little less than a millimeter thick. So it's, you know, you can probably see it wiggle in there a little bit. So that's the reason for these large diameter flanges here, is to support it out as far as you can. Now, these are surprisingly durable, and you know, you're guiding it on the machine, so if you don't get hairball with the thing, you know, they work great actually. So so what I'm going to do is I'll fire it up and I'm going to dress the edge a little bit. I'm going to use a Norton Norbide stick, and this is a it's on the tip of my tongue. I can't think of. Anyway, it's God dang it, Tom. What is what is this material? All right, I'm sorry. I just can't think of what this is. It's boron nitride, but it's a different. Is it boron nitride? Yeah. Okay. Anyway, this is killing me. Anyway, Norby, look it up. I'm sorry. Anyway, we're just going to dress it by hand here just to kind of open up the abrasive a little bit. And, oh, God. Anyway, open it up a little bit, and then we'll touch off, and we'll pick up our edge. And we're going to, you know what? I'm just going to start doing it here. We're going to pick up the side first. And this is just going to be an audible pickup right there. Okay. Come up. Alright, and I'm going to make a mark on my my cross feed here. So what I want to dial out the half of the blade thickness first, okay? Alright, so then we're going to dial in our offset for our first cut, which is 90 thousandths off of this edge. 85, okay. Alright. And then what we want to do, let's just do a visual, yeah, that's about right. Now what we want to do is pick up the surface of that. Very gingerly. So you got to kind of scrub over the whole surface because there may be some high spots. Okay, it looks like it's just kissing down right there. Where we at here? Let's put on another towel. Okay, so there's a good pickup there. All right. And now we're going to set up our coolant, because with this guy here, coolant is mandatory. Okay, so don't even try it without coolant. Okay. All right, I think we're ready here. Get some juice flowing here. Alright, so now we're going to dial in. So we're going to do this in two shots, 25 thousandths deep per shot. There's the first one. Alright, and then we're just gonna creep feed this. Use a little bit of brake action here. Oh, you see, it's just dicing right through there like cream cheese. Now the feed direction is important on this. You don't want to climb cut doing this, okay? Actually, I'm gonna get a little more juice going here. And it's surprising how little wear on the diameter you get doing this, okay? I'm always shocked at how little it is, alright? So there's 25 thousandths right there. Okay. Alright, so that's looking pretty good. So I did lose some diameter on the wheel, so I had to go back through it a couple of times to get them all evened up. Not a fussy dimension, you just want them to kind of visually look alike, otherwise you look like a bozo, right? So I'm going to clean off the dicom here and dress it up a little bit, and then this is going to go in a shipping box to Mr. Robin Renzetti, who I am working with on some heat treating stuff. So anyway, we'll see that again shortly. Get this thing off. All right. Oh yeah, look at all the goobies on there. All right, so there's the grooved platen. I'm going to leave the other side plain, and we'll lap that and make it a ringable surface, and so will this. But this will have grooves in it, so there it is.